Hello everyone, welcome back to Educational Era. Today we will be talking about energies associated with simple harmonic motion. We will be going over kinetic energy, potential energy, and total energy, which is the sum of kinetic energy and potential energy. Alright, so let's get right into it. So, kinetic energy. To derive the equation for kinetic energy, we need to go way back when we learned kinetic energy. We know that kinetic energy is going to be half of mass times velocity square, and for velocity we know that velocity of simple pendulum is going to be r omega cos omega t, that is going to be omega r square minus y square. So if we replace it right here, we will get that kinetic energy is half of m omega under root r square minus y square whole square, that is half of m omega square r square minus half of m omega square minus into y square. That is our first equation right there, and the derivation for kinetic energy. Now let's move on to potential energy. Potential energy is a little bit tricky to derive. So potential energy, for potential energy, let's take a pendulum. A pendulum is right here, right? And let's say this pendulum moves from here up till here. Let's say it moves up till here, right? And that is our distance y. Now let's say in this moment there is a time when pendulum is right here and it moves a small distance from here to here, and this small distance is going to be dy. All right, now potential energy can easily be obtained from work done, right? So we know that work done is force times displacement. But in this case, if you look at this figure right here, the acceleration of the pendulum is maximum when it is at its mean position, from what we discussed in our previous video, and minimum when the acceleration is acceleration is 0 when the pendulum is at its maximum position. So that would mean that the acceleration is decreasing as we move from mean position to its maximum position, right? So that would mean that force applied is in opposite direction from the moment of the pendulum, right? Think about it, right? So our work done is force times displacement, but the force and the displacement acting on the force due to the force is opposite in direction. That is why our work done is going to be negative. First you need to know this. Now force is going to be F and our displacement is going to be dy. Now let's now if you see this right here, force times displacement is really small quantity, right? Force times really small quantity is going to be a really small work done too. So we will write small work done. Now if we integrate this from 0 to y, then we will get integration of from 0 to y of dw small work done is going to be our integration of from 0 to y force dy, right, and negative. Now if I simplify this, work done is going to be minus integration of y f dy. I wrote this again because let's think about it. Force is mass times acceleration, and we know that acceleration of simple pendulum is minus omega square y, right? So let's write this down. So force is going to be minus m omega square y. Keep that in mind, and I'll replace it right here. Let me use the green color. Minus integration of 0 to y minus m omega square y dy. Now if we write it here, work done is going to be, let's pull these three out from here, and integration of y from integration of y dy is our y square by 2, right? Integration of 0 to y dy is y square by 2, right, from 0 to y. So let's write that down. M omega square y square y m omega square integration of 0 to y dx, right? So if we write this down, simplify this even further to this, we will get half of m omega square y square. So this right here is our potential energy. Now we have our kinetic energy and we have our potential energy. So the total energy is simply the sum of kinetic energy and potential energy. So if we write it down here, total energy is going to be our kinetic energy, which is this right here. So 1 by 2 m omega square r square minus 1 by 2 m omega square y square. Let's write that down. 1 by 2 m omega square r square minus 1 by 2 m omega square y square, and our potential energy is 1 by 2 m omega square y square. So plus half of m omega square y square. Now if you see, there are two common terms, so if we cut this down, we'll get that our total energy or our mechanical energy is 1 by 2 m omega square r square for throughout the simple harmonic motion. Now if you see this equation right here, if you see this equation, mass is constant, omega is our angular velocity is constant, and our r is our amplitude, which is also constant. So the total energy throughout the system remains constant. So if we plot the graph, let's look at some special cases first and we will plot the graph. Alright, so some special cases. First special cases, first we'll see at mean position. Kinetic energy is half of m. Kinetic energy is half of m omega square r square minus y square, right? So in mean position, our displacement is going to be 0. So kinetic energy is going to be half of m omega square r square. Likewise, our potential energy is half of m omega square y square, right? And again displacement is 0, so our potential energy is going to be 0. So total energy is again going to be the sum, that is again half of m omega square r square. Likewise, let's say at maximum displacement, that is when y is r, kinetic energy is again half of m omega square r square minus y square. In this case y is r, so r square minus r square. So our kinetic energy at maximum displacement is 0, and our potential energy at maximum displacement is going to be half of m omega square y square, and y is again r, so half of m omega square y square, and that is half of m omega square r square. So the total energy again is going to be 0 plus half of m omega square r square, so that is half of m omega square r square. So the total energy is the same throughout the system, right? Now if we plot the graph, so this is our graph, right? And this is going to be energy, and this is our going to be displacement. Now we know that total energy is always constant, so let's say here is our going to be our total energy, and it is going to be constant throughout the oscillation. And now if we look at our previous cases, kinetic energy at our mean position is going to be maximum, right? So let's say at this 0 is our mean position, and this is our maximum position. So at mean position kinetic energy is maximum and potential energy is 0. So kinetic energy, let me draw with a different color. So kinetic energy is going to be maximum. Here is going to be our kinetic energy, and here is going to be our potential energy, and in mean position kinetic energy is maximum. Likewise, if we look at our maximum displacement, at maximum displacement kinetic energy is 0. So the kinetic energy is maximum at mean position, and at maximum displacement kinetic energy is 0. So it is going to be plotted this way, right? Now from maximum displacement, again from maximum displacement, the body is going to oscillate to its mean position, let's say at 0. So this is again going to be up till here, right? Kinetic energy is again going to start to increase up until when it's going to be maximum here. And for our potential energy is going to be 0 at our mean position, and it is going to be maximum at our maximum position. So it's going to look like this, and again at our mean position potential energy is going to be 0. Yeah, right there, that is the graph for our total energy, where this blue one is our potential energy and this green one is our kinetic energy. Now it should be clear through this graph itself, right? So as the displacement increases, as the body oscillates, the total energy remains constant. The kinetic energy is maximum at the mean position, and it decreases up till the maximum, and again starts to increase up till the mean position. And the potential energy is 0 at its mean position and increases up till the maximum displacement, and again decreases up till its mean position. So this This will continue throughout, again and again, throughout the oscillation. Yeah, that is all for today. Thank you so much for watching. We did discuss a lot this time and we derived a lot of equations, but you only need these three equations of kinetic energy, potential energy, and total energy. Yeah, so that is all. Thank you so much for watching. Make sure to like and subscribe, and in our next video we will go through the application of simple harmonic motion, where we will talk about springs and derive some equations for horizontal springs and so on. Yeah, so thank you so much for watching.